Welcome back, everybody. Today we're going to talk more about operators and how to manipulate operators, such as squaring them and formulating new operators in our last problem here today. So operators, as we know, extract information from our eigenfunction, but we can formulate new operators by manipulating the ones that we currently know. So here we have a question: what is the operator a squared? So if we apply it twice to our eigenfunction. And let's say our operator is the first derivative with respect to x. So as we know, if we apply a onto our eigenfunction, and if it's an eigenfunction, we'll extract an eigenvalue, or the information we observe, multiplied by that eigenfunction in the end. That is the basis of operators, eigenfunctions, and eigenvalues. Now, if we're applying the operator twice to our eigenfunction, this is essentially the same thing as saying the operator a squared operating on our eigenfunction. So let's try to find it by using this formalism here on the bottom. So we know this is going to be true, and this is how we're going to end up finding it. So we're going to apply it once to our function and then apply it a second time. So we know our operator here is the first derivative with respect to x. So if we apply it twice to our function, we're just going to apply the first derivative twice, d over dx, applying onto our f of x. And this is more commonly known as our second derivative. So d squared all over dx squared of our function f of x. Very simple, very easy, but when we add more terms into our operators, this can become a little bit more complex. Before I move on to some more practice, please show your support for this channel by liking and subscribing, as all I want to do is help support students on their learning journey. Let's move on to more of a difficult problem. Here we're going to have our operator of d over dx plus 1. It doesn't seem very difficult, but it actually adds a little bit more complexity into squaring our operators. So here we're going to apply our operator twice onto our function again. And so this time we're going to have d over dx plus 1, d over dx plus 1, operating on our function f of x. The first thing that you should do is distribute your function to your first operator. So let's do that first. So this would be equal to d over dx plus 1 multiplied by df over dx plus f of x. So let's distribute out our two quantities while retaining the order, because order sometimes will matter. Let's not swap around any of our operations. Here we're going to have d over dx times d over dx of f plus d over dx applied on f of x. And now we're going to distribute out our 1, or we're going to get d all over dx applied on f of x plus f of x. So we can combine like terms, and we can see the two terms in the middle are the same. So here, two derivatives applied on our f of x is the same thing as saying the second derivative with respect to x plus 2 times d over dx plus 1, all applied onto our f of x function. I ended up combining our specific operations and also factoring out that f of x function in the same step. This is where we end up getting our operator, where we can see that a squared is the same thing as saying d all over dx, second derivative, plus 2 d over dx plus 1. So this is actually how you find the square operator for a more complex problem. Let's move on to another practice problem, where it's going to be even more complicated. So here our operator actually has a lot more x terms, so this is actually going to involve a lot of the product rule. So we're going to see that here now. So we're going to apply our operator twice on our eigenfunction. We're going to have x times d over dx plus x times d over dx plus x. And again, the order matters that we apply this, and we have to go from left to right. So if we apply this f of x onto these two terms, we're going to have x d over dx plus x multiplied by x d over dx of f of x plus x times f of x. And so now let's distribute out our terms even more. while retaining all of the orders from before. So with this first term, which I'm going to designate here in blue with this blue dot, we'll write it out in blue. We're going to have x times d over dx applied onto x times d over dx of f of x. So that's our first term. And then the second term involving that blue dot is x d over dx x f of x. So that's our second term dealing with that blue dot. Now the third and fourth terms will indicate with this green dot, just for bookkeeping. We're going to have x times x, so x squared, d over dx of f of x. And then our second term plus x squared f of x. So the green terms are actually in a state that we can keep them in. Meanwhile, when we're going to have derivatives of functions or two functions that are products with respect to x, we actually need to endorse the power rule here. In a previous video, I talk about how we actually derive the power rule if you're interested as well. So let's take a look at this first quantity and see what this will end up looking like. Here we're going to have x multiply the quantity of the derivative of this prospective function, where we have one quantity which is just x, which is our first function. Then we also have f prime of x as our second function. And we know the derivative of two functions with respect to x, ax times bx, is the same thing as saying a prime of x, bx, plus a of x, b prime of x. So let's apply that to here. First, we're going to take the derivative of our x term, which is just going to be 1, multiplied by the same function of the second one, so d over dx of f of x. So we're good here. The second term, we're going to retain our x term and take the derivative of d over dx of f of x, which would end up being d over dx squared. So the second derivative with respect to f of x. So everything multiplied by x. Now let's do the same thing for the second term, where this term here will be plus x times a different quantity this time. We're going to take the derivative of x, f of x, where we're going to have 1 for our x, and then our f of x will retain, plus, now we'll keep x by itself, and we'll take the derivative of f of x, so d over dx of f of x. And then we'll retain the two terms here in green and bring them down below. Plus x squared, d over dx, f of x, plus x squared, f of x. So now let's work on distributing out these x's and combining all of these like terms. So here, we're going to end up having x d over dx of f of x plus x squared, the second derivative of f of x plus x times f of x plus x squared d over dx f of x plus x squared d over dx f of x plus x squared f of x. So this is actually where it can get complicated really, really quickly. And this is why you have to write all of these terms out and see what you can end up combining. We can see these two terms are the exact same, so we'll combine those two terms and just make a 2 coefficient in front. And those are the only two terms that seem to be the same. So here, we're going to end up having x d over dx plus x squared d squared over dx squared plus x plus 2x squared d over dx plus x squared, all applying onto our f of x function. So everything in here in the parentheses is going to be our operator a squared. And so I'll write it out above as our final answer. A squared is the same thing as saying x d over dx plus x squared d squared over dx squared plus 2x squared d over dx plus x squared plus x as our final a squared operator. Now, let's work on manipulating and formulating different operators from existing and classically known quantities. So here, we're going to look at finding the kinetic energy operator, that we'll actually be using for our Schrodinger equation, especially model systems such as particle in a box, by relating to classical quantities such as momenta and kinetic energy. So first, we want to find the kinetic energy operator, which is usually denoted as T with our caret sign. This might be different depending on the textbook that you end up using for your specific class. We know our kinetic energy value is usually found by doing 1/2 mv squared. But usually we need to relate it to momenta, as we have an operator that relates to momenta in our quantum mechanics, and especially within this problem here. So we want to get kinetic energy into units of momentum instead of mass and velocity. So we know momentum is the same thing as saying m times v, or mass times velocity, and we know we have mv within our formula here. So if we square momentum, we end up getting m squared v squared, right? And we have most of those terms within our kinetic energy value. But we know we only have m v squared. So p squared divided by m, if we divide it by m on both sides, we know we can get mv squared. So if we plug that in into our quantity right there, write it down here below, we can see that kinetic energy is the same thing as saying the momentum squared divided by 2m. And this is very important because our quantum mechanic operators are related to our classical mechanic values. So if we want to find our kinetic energy operator, we'll have to use our momentum operator as well in order to solve for our kinetic energy. If we can see here, we have our momentum operator within our problem here. So all we have to do is square this momentum operator in order to solve for our kinetic energy operator as well. So let's do the same thing that we did before, where we're going to have 1/2m, which is going to be factored out, multiplied by p and p, which is our momentum operator, applying onto f of x. And we know the momentum operator is the same thing as saying minus I h bar, where h bar is the same thing as saying h over 2 pi, like in general chemistry. So this quantity will simplify to 1/2m, and we'll apply our operators here. We have minus I h bar d over dx, and minus I h bar d over dx of f of x. We know our I and h bar are constants in this case, where I is also the square root of -1. So when we apply them together, we're going to end up getting I squared h bar squared all over 2m. And we're just going to apply our first derivative twice to our f of x function. And like we talked about before, it's the same thing as saying the second derivative. And as we know, I is the same thing as saying the square root of -1 of -1. So I squared is the same thing as saying -1. So if we apply that rule, we'll see that the kinetic energy operator is the same thing as saying minus h bar squared all over 2m, applying d over dx squared, multiplied by our f of x. And one common notation that I should have put within this problem is that this really should be t of f of x if we want to make this equal. If we want to make this equal, but here it's okay to keep going with this, because as we know, our kinetic energy operator is the same thing as saying minus h bar squared all over 2m d squared all over dx squared. And you will see this within the Schrodinger equation, and this will actually be the only operator applied for the Schrodinger equation for a particle in a box. I hope you have learned something here today. Please comment down below if you have, and any questions you may have about manipulating operators, such as squaring them and also applying them to create new operators as well. Have a great day.